Okay, so this is a demo of the Lab 4. In the Lab 4, we were asked to use the quick select to find the kth list elements of any given array, and the average running time of the algorithm should be linear. So if we go through the basically the code and we run it, this is what it should do. So basically the user is asked for a number that will be used for the size of the array, and once this number is entered in the variable n, basically n random numbers are going to be generated, and these random numbers are going to be ranging between -100 and 100, and then we're going to print the array A. So I'm going to enter a size, so like 6 for example, and so as you can see, the array is it has 6 elements, and basically I chose to display it in this way so that it's easier for the user to see which index they can pick, because the next line is asking them to pick a number that is going to be used for the kth list element, and so basically displaying I equals 0, I equals 1 helps with for the user to see. Obviously this might slow down the program, but it's better for display purposes. So we're gonna enter index 3, and so the function that gets the kth list element runs, and when you basically the function uses quick select, and quick select is based on quick sort. So that's what we're using, and then we are going to enter another number for the kth max element. So let's say 4, and it's going to return the maximum numbers of an array of the maximum numbers, which is in this case 54, 19, 0, -4. And as I mentioned, the code is there's like a function, the find max numbers, which gets the array and also the index, but -1. So these two elements are going to be passed to the find max elements, and you can see that I'm using partition because quick sort, as I mentioned, quick select is based on quick sort, and also the swapping function that we've seen in Lab 3. And so, yeah, and this is the function to generate random numbers, and pretty much that is for the Lab 4, and most of the code, the rest of the code is in the PDF that I'm going to attach. And now moving on to Lab 5. So for Lab 5, we were asked to to calculate the maximum subsequence sum. And so the maximum subsequence sum, basically you have like an array of numbers, and you're basically going to find the maximum sum that can be that you can get from that array, from numbers that are successively that have like subsequent order, basically like that have index that are right next to each other. So like index subsequent indexes, basically. Sorry. And so what we're gonna do is we're going to ask the user again to enter a size for the array. So let's say we enter 7. well, this went too fast, but we're going to scroll back. And so what we have here is, so we have the user who entered 7, and an array is generated, an array of numbers between -100 and 100, 7 numbers are generated. And so what we're going to do, as I mentioned, is in this array here, what are adjacent numbers, I guess, adjacent numbers that have the maximum sum. So in here we see that it's probably going to be 5283, like something in the middle here, the sum of these numbers here. So what's going to happen is it's going to, and it's part of the algorithm, like the function get MMS linear. Here I'll put it up. And so as you can see, the array of numbers that we generated is passed along with the size. And then this for loop here is the for loop that we have going on here. So this for loop, we're going to keep track of 2 pointers, if we can call them like that. So we have the left and the right, and so 38 and -99. So we're going to compare. They're going to be compared, and every time the sum that is made is greater than what we had before, then there's going to be an update. So for example, we have 38 and -91. So it's going to remain like that because -91 is not it's not greater than 38, and then so we keep 38 because that's what we're going to keep. And so we have 38 and -3, and then we get 52, and after that we're going to have the maximum sum of 135, and as I had mentioned, it's going to be this here because that's the largest sum that you can get. These are the largest positive numbers that we can get that are just next to each other. So that was lab 5. Essentially, there is also, so this method that I just described has a running time of n log n, and the first method that we use to find here has a linear time, and this can be seen in the code, but for the purpose of the demo, I'll just keep it short. As I had mentioned, so we get the array A and its size, and so we're going to have a temporary variable, and this temporary variable is going to be used to basically add the current index with what is being calculated. We're also going to consider a case, like whenever the sum is negative, we're going to reset it to 0 because we don't want a negative sum. We want the highest sum. And every time the sum that we get is greater than the one that we had, we're going to update it, and this is what we have here. And after that, it's going to return the maximum sum. And then we have the other method, which is n log n, that is the running time. And then it's basically going to take the array A, and we have our base case where there's only one element in the array. And then we also have our, we're going to basically get the midpoint of, we're going to check what is the midpoint. And then after that, we're going to consider a pointer for the left of the array, and then also the right. and then after that, it's basically going to find the maximum of the left that starts with our x here and ends with the midpoint. And then same here, it's going to find the maximum of the right side of the array, which begins with n plus 1 and ends with y. And here we have our array to print. Sorry, we have our function to print the array. And then we also have our function to generate a random number in a range. And that is the end of the lab 5. And then for the lab 6, we were asked to do a heap sort, and also to heapify. And just as a review, heap sort is one of the best sorting methods, and in the case of we have like two cases. We have a mean heap and then we have a max heap. In a mean heap, basically we're going to try to push the element with the lowest value that is determined at the top, at the root of the tree. Or we're going to, in the case of a max heap, we're going to have the element with the largest value at the top. So that is what we're going to use those methods. And if we run lab 6, so we do the same thing as in the previous labs, where we ask the user to enter a number. I'm going to say 7 because 7 is a lucky number. Okay, so I entered 7. What is happening? What is happening is that so an array of 7 elements is generated, and we're going to try to find the running time of heap sort and insertion sort. So first we're going to call heap sort to sort the array, and then our heap sort is function it was at the top. Okay, yeah. So it was at the top. So our heap sort function is going to be based on the array that has random numbers, and it's going to sort the array in the heap with running time n log n. So there's basically going to be swapping, like it's going to check at each element if it has if it has a bigger value, it's going to be pushed at the top of the heap. And to do this, we're going to use 3 functions: the build max heap, the swapping one, and then the max heapify. And the build max heap, the way it works is that it's going to build our array it's going to build our max heap based off the array A. And to do this, it's going to use the max heapify function. And the max heapify function, we're going to use again the array A, its size, and index, which is the current location where we are in the array. And there's going to be a comparison. Well, first of all, we're going to need to represent the tree in a way, or the heap, and we're going to use these 3 variables. We're going to use the max index, the left, right, and we're going to compare. If the left child is larger than the root, the max is going to be the left, which makes sense. And then if it's the right one that is larger than the root, then the max is the right, which is updated here.